Last talk for this morning is Gregor Masbaum from GSU, talking about, as you see, Alexander-Conway polynomial, milnor numbers, etc.
Okay, thank you very much. So it's a great pleasure for me to be here, and I would like to thank Malek for inviting me. Unfortunately, I never had the privilege of meeting Pierre Leroux. So this is a very new crowd for me. I'm not a combinatorialist or graph theorist or statistical mechanic in any way. I'm really a topologist. So please allow me to use some words in maybe a slightly different way, but I hope will be understandable. And so I'm here because somehow during doing some topology, Arkady Weintraub and I, we apparently discovered this Pfaffian matrix tree theorem. So I want to talk about this a little bit, and I want to show you where this came from. So there will be a little bit of topology, in fact, not theory. And I will mainly use the blackboard. So yeah, and I'm sorry? Mainly. Well, I will show you a transparency at some point, but and I have some good or bad news according to taste. So this is actually a 1 hour talk. So according to the program. So you shouldn't be surprised if I keep going on after 45 minutes. And just complain to the organizers about this. But anyway, if people want to leave, I will not be offended. Okay, so as I said, this is joint work with Arkady Weintraub. He's at the University of Oregon, and it's in some sense already old. So this sort of a combinatorial version is published here, and sort of the topological piece is published there. So it's like 5-6 years old, but there have been some recent developments, and I will try to talk about them. Anyway, so let me just remind you of the classical matrix T theorem. And I just write MTT. So it was already on the board yesterday. And I just do this for the complete graph. So for what I think you guys call Kn, or Km. Actually, I want to use Mn for some other thing. So, and then I can just say, well, I look at this Laplacian matrix. So L, which is basically just has entries xij. So ij from 1 to m. And then they are symmetric. So xij is xji. And I really don't have the diagonals. And in fact, for the diagonals, I'm going to take xii equal to minus the sum over the xik's, where k is different from I. And this is really the Laplacian matrix for this complete graph. And then the theorem says that if you take the determinant, in fact, I should probably take a minus sign here, the determinant of this matrix L. I take out any line or column. So this means take out ith line and column. I hope you can read this. Can you read this? Then this is sum over spanning trees. So this is a spanning tree polynomial of this Kn. So for example, if we have K3, so then 1, 2, 3, then you would have, for example, for this spanning tree 1, 2, 3, you would have the monomial x12, x23. Okay? And there are no signs. So if we like, we can call this thing, we can give it a name, k sub m. And so this is a homogeneous polynomial of degree, so this should be m, I'm sorry. Homogeneous polynomial of degree m minus 1 in those xij's. So Xavier says he maybe doesn't like this notation, but I will write it like this. So homogeneous polynomial of degree m minus 1. In these symmetric variables, here I just write S2, say of Rm. So here the bases are these xij's. And then I take homogeneous polynomials of degree m minus 1.
some of those inclusion, some of those memberships must be included.
I'm sorry?
You have element of.
No, this km is a polynomial of degree m minus 1 in these variables xij.
Oh, I'm sorry.
So I view this.
Script km.
Is different from this. This is the complete graph, and this is this polynomial. So km of these variables xij. I'm sorry?
The first element of.
I'm sorry. Thank you.
Okay.
Sorry. Okay. So anyway, so this is, and I mean, you all know this, and okay. So what is the Pfaffian theorem? So I mean, I was wondering how should I do this? Should I just tell you how we found this, or should I just make sure you actually get the statement? And so I will just do the statement at the very beginning. So what I'm going to do is, so the Pfaffian MTT. So what I'm going to do is I'm going to take, so this was minus this matrix. I'm going to take, now I'm taking in these variables, so indeterminates yijk. And again, 1 less or equal ijk less or equal m. But they should be skew symmetric. So it means if I do y, sigma I, sigma j, sigma k, this should be minus 1 to the sigma, which is the sign of the permutation sigma, yijk. That's what it means. Sigma permutation of 3 letters. So in particular, there's no yi something. They're all 0. And then I take lambda, following matrix, just the matrix with entries lambda ij. And what I take as lambda ij will be just the sum over k of these yijks. So that's a skew symmetric matrix. And the theorem is so this is, so together apparently we discovered this with Weintraub, is that if I take the Pfaffian, in fact I will take minus 1 to the I minus 1 Pfaffian of this matrix, where I take out again the ith line and ith column. This is equal to the spanning tree generating function polynomial on the complete free regular hypergraph. So this is something I will just call 3 graph. And so what are these things?
Excuse me.
Yes?
In the sum in the middle of the board, do you want k to be different from k can be anything?
K can be anything.
Because if I is equal to j and k is equal to I.
I'm sorry? Then some of them are 0, but I said that.
But I is non-zero, right?
I is also 0, according to this.
If 2 indices are the same, it's 0.
It's 0.
Yeah, but
What's that permutation?
if all three.
So what is a 3 graph? So I just have a set of vertices and a set of edges. So usually an edge has exactly 2 vertices, but now I wanted to have 3. So E is just a collection of 3-element subsets of V. That's it. So in hypergraph, 3 regular, so every edge has the same cardinality, and there this is 3. So here's an example of a 3 graph. So this thing has 9 vertices, and it has 4 edges. And every edge has indeed 3 vertices, so the edges are yellow. The vertices are these. So some people would call them.
The edges.
You cannot see the yellow?
You're right. Can you do it in red? You have a red chalk there.
I thought the yellow was actually visible.
It is, but it's identical to white.
Okay, but anyway, I think that's good enough. So an edge will be drawn something like this. So some people use cacti and would draw this like this with a polygon. So So it's somehow the same thing. But for some reason, I want these diagrams to look like this.
You just need to slow down.
I'm sorry? And you see, this thing I would actually call a tree, and in fact, it's a spanning. So the notion of tree is kind of obvious. You just realize this thing topologically, and it should be a tree. So something that would not be a tree, for example, if you have 4 vertices and you do something like this. I will use yellow, although Alan can see it. If you do something like this, this is not a tree.
So in a tree, the triples are almost disjoint.
Yes. And in fact, if you have a tree will implies that the number of vertices is odd, which you easily prove by induction. So in this theorem, actually, if m is not odd, so I may as well assume m is odd, because the right-hand side is going to be 0 if m is even. There are no spanning trees. Also, the left-hand side is going to be 0, because this is an m by m matrix. If m is odd, m minus 1 is, if m is even, m minus 1 is odd, and then the skew-symmetric matrix will have 0 determinant, and so the Pfaffian is the square root of the determinant. So maybe I should write this once. So the determinant of this lambda I is the Pfaffian of this lambda I squared.
Excuse me, just a really silly question, but does the edge ijk take a weight yijk or
No. No. We are going to talk about this in a minute, but right now this is the definition, just 3-element subsets. Okay. So let me just look at an example. So what happens for m equal to 3? There's really just one thing you can do. 1, 2, 3. So we'll get y1, 2, 3. This is this polynomial P3. But on the other hand, if you now look at the Pfaffian of this matrix, so it's what is this matrix? So the entry here, the 0, 0 something entry is 0. Actually, all diagonal entries are 0. Here, the only thing you can write is 1, 2, 3. Here, the only thing you can write is 2, 1, 3. This I take out anyway. And the Pfaffian is indeed y1, 2, 3. And y1, 2, 3 is minus y2, 1, 3. So the determinant of this thing is y1, 2, 3. Sorry, minus y1, 2, 3. Anyway, you know how to compute the determinant. Because this is minus this, it fits. Okay. Now what happens for m equal to 5? Well, then if you just write down this matrix, try to do the determinant of maple, it will say overflow. There are already too many terms. But in fact, it's very small. So what happens is that this P5, well, there will be one term which is y1, 2, 3, y3, 4, 5. And this would correspond to this graph. So I have my vertices 1, 2, 3, 4, 5. And then I have a spanning tree in yellow, which would be like this. So I'll say I take together those, and I take together those. And then there are 14 more. Because you see, how many are there? Well, you have to somehow choose one vertex. In this case, the combinatorial type is unique for m equal 5. One vertex which has 2 of them. So there's 5 possibilities, and then there are 3 to choose the other one in pairs. So there are 15 in all.
So your convention for taking the weights is that for each.
I'm going to explain.
Okay,
So there's as Christian points out, there is some problem here. Why do I write this? Why don't I write 2, 1, 3? Very good question. I was going to explain. So how to write this thing? So let's do this example here. So what I would write to so the monomial. If this is my spanning tree, and again, in the spanning tree there is no information about some ordering here.
So put your point on the triples which are edges.
Wait a minute. Let me just do it my way, and then you can comment on it. Okay? So what the monomial y to the t, well, up to some sign, it will just be y1, 3, 5, y5, 4, 5, 6, y2, 7, 5, y789. So up to some sign, it will certainly be this.
And what is y to be?
So that, I mean the monomial associated to this tree.
Oh, okay.
Maybe y sub t. So in this formula, I should write this as sum over al minus 1. I mean sum over y sub t. T are these spanning trees. Okay. So how would I do this? So basically, what happened is I made a choice. For each of these 3-element subsets, I made a choice of a cyclic permutation. So I chose this one rather than so I chose 135 here rather than choosing 315. Now, there's no embedding information here. I don't have a cyclic orientation here. Okay? So what I do is I just do the following. I make this choice. So I have choose 3 cycles, say I sub e, j sub e, k sub e for every edge. So here are my 3 cycles. So these are 3 cycles in the symmetric group on m letters. Now I take the product, and maybe let me do this over here where they have some more space. Yes, but there's already something on them. So then I look at the product of these 3 cycles. So I take the product in any order actually of these I, E, J, E, K, E, and then little lemma. This is going to be an M cycle, exactly if and only if this thing is a tree. So this is actually an M cycle. So you can write this thing as S of 1, S of 2, up to S of M in the cycle notation, where S is something, some permutation. And it's the sign of this permutation.
And you mean that you
So you can write this as also as S, and then there's this standard cycle S inverse. So it depends on the choice that I declared that this is my standard M cycle.
M was the number of vertices?
M is the number of vertices.
so there's a product of permutations, which
Yes.
and this holds for every sequence because it's order dependent in principle.
Yes.
But the
What's your
statement-
question?
So for every ordering,
Yes, the sign is independent of how I do this product. But it's not the sign of the M cycle I get, because it would always be even because M is odd. So it's a little bit subtle here, but that's the answer. And now you can see that if you chose a different one here.
It's not the sign of that M cycle. You're right. 'cause
No.
that would all- So what is it the sign of?
It's the sign of this permutation S.
Ah, it puts the M cycle into the standard order.
So there is a graphical way to do this, which can be read in the paper, but I will not do it now. I've made some choices what I do, what I don't do. So this is the definition. So what you will find, for example, if you do P5, which is already written here. So the next one, for example, if I want to do Y124, Y435, this would actually appear, I would have to put a minus sign. And then plus 13 more. This is what comes out when you do the computation. And this is the answer. This is the whole theorem. So I could stop here.
So if I understand it well, it really, you are saying that it doesn't matter how you associate, that it doesn't change the sign.
Yes. So I'm saying the thing has nothing to do with cyclic orientations. And indeed, so in the beginning I thought maybe one has to use oriented edges or something like this. But it's not true. In the sum, for every tree there is just one monomial. So the monomial really should, if things are correct, should be associated really to the tree without any further information. And that's a claim is the case. The only choice that was made is the choice of this n cycle here, which corresponds of the order of the entries in my matrix also, of course. So it's consistent. Okay, so what about proofs? I mean, it's a bit like this Kirchhoff, your original theorem. I mean, once you know the statement, you can make your own proof. So we actually gave two proofs. So the first one with contraction deletion. And I mean, you can prove so it's the same story. You have your tree. This polynomial will satisfy some, so you have some edge here. And then you have some other stuff. Say this is 1, 2, 3. So we'll have the PM. Say in variables 1, 2, 3, 4 up to m. You can write this. One term is PM, where you just put 1, 2, 3 equal to 0. So that counts all the trees that do not contain this edge. And then there will be another term which does contain it. So write 1, 2, 3. And then you have some PM minus 2. But then somehow this was contracted. So now you have some very fat vertex here with index, say, 0. And you have these things sitting on it. So you would have to take PM minus 2 of 0 and then 4, 5 up to m. But that wouldn't be right. And then in this thing, you have to substitute, so for 0, you have to substitute 1, 2, and 3 and take the sum. I mean, you can formulate this in many ways, but this is one way to formulate it, which I will actually use. So for example, I can derive this thing with respect to y1, 2, 3 if I want, and I can see what the answer is.
So what do you mean 0, 1, 2, 3 are labels?
So it means that so this would be something, the vertex sets are the original ones from 4 to m, and there is this new guy which I call 0 after contracting 1, 2, 3. And now any tree on this guy, they will have somewhere there will be index 0, many in several monomials. And then this index 0 has to be replaced by 1, by 2, and by 3. And each time I will get a legal spanning tree on the original one. I mean, it's the same story as the usual contraction deletion relation.
But I don't understand. What's the point of these labels?
Is that the labels induce the weights?
Okay, so if you like, one thing, I mean, again, Xavier will not like it, but I would like to think of this PM as an element, a homogeneous polynomial of degree now have degree m minus 1 over 2, because this is the number of edges, of lambda 3 of Rm. And so these are my labels 1, 2 up to m. And so if I do Pm minus 2, I will only have m minus 2 labels. And one of them I want to call 0 because it came from this contraction of 1, 2, and 3. Anyway, there's nothing non-trivial going on here. It's just the usual contraction deletion relation. Okay. So sorry,
Oh, well, why? I see, because 0 is going to become part of some other hyperedges.
Yeah.
And you have to successively replace it
Yeah.
by 2 or by 3.
When you contract, you keep the parity, right?
I'm sorry? Yeah.
Contract, you keep
Yes.
the parity.
Yes. So anyway, let me just wipe this out again.
It happens for graphs with deletion contraction. You just don't see it.
So this is the original proof, but then there is a proof by topology, and I actually want to explain this a little bit. So this is actually how we found this. But then there is a very nice proof, so I don't know which one was first. So let's say up this lam, which does it with Grassmann-Berezin calculus. And then if I understand correctly, this was a very much generalized so first of all, he generalized it also to higher kinds of hyperedges. But I'm not going to talk about it. And then there is, this was then generalized in this amazing paper by 5 authors, which I wrote down somewhere. CJSSS, and most of them are here. So Caracciolo, Jacobsen, Saleur, Sportiello, Sokal, something like this. So,
Did we generalize it?
but I'm not quite sure. But anyway, this Grassmann-Berezin, anyway, I'm just sort of doing the easiest case of something.
I didn't know that our theorem contained yours.
I'm sorry?
I didn't know that our theorem
Yeah,
contained yours.
anyway, I just wanted to mention this. because I think this is very nice.
I mean,
And-
it is very nice, but I didn't know it contained you.
And there is something by Hirschman and Reiner. So they prove it using a sign reversing involution. And maybe this is for combinatorists the most satisfying one. I don't know. I'm not a combinatorist.
I agree.
This implies something.
Huh?
I agree with the
So it means there is this huge cancellation going on, but somehow you can really pair up the guys that are cancelled. So yeah. And of course, what I should say is, I mean, I won't even write it down. You can make a version of this for a general 3 graph. I mean, like the usual thing, I just formulated for the complete one, but if you know for the complete one, you can write it down for any. I will not bother to do this.
You just set a bunch of weights to 0.
Yes. Yeah, it's absolutely equivalent. So what have we done? In some sense, we have just explained one little thing, namely this. So there's a classical theorem. You have ordinary graphs. You get a sum over trees, spanning trees. I forgot to say spanning trees. I'm sorry. And then for these 3 graphs, the edges look like this. You have a Pfaffian tree. Pfaffian tree theorem. Now I want to explain how this came about. So the first thing is, I guess, well, I won't do this sexy stuff. So just striptease. Just show you the whole thing, what we somehow... Anyway, let's just leave it down. So where did it come from? So it really came from, I'm really a topologist. So it came from quantum topology. So how to say this? So finite type invariance of links. So this is also Vasilyev invariance of links. Okay. So what is a link? So disjointly embedded, oriented circles, and also ordered. I know which one is the first one, which one is the second one, and so on, in R3, or a topologist would say actually S3. It doesn't really make much difference. And usually I call M the number of components, so it's the same M. So and I write such a thing as, say, L1 union L2 union LM. But I mean, the union sign doesn't really take into account how it's linked. And if M is 1, it's called a knot. So for historical reasons. So here are some examples. And then what is the first sort of invariant of these things you can do? It's really the linking number. And what is the linking number? So the linking number of L1 and L2, this would be actually, I take L1 and now I write dot sigma 2. So sigma 2, this is an oriented surface with boundary of sigma 2 equal to L2. And this dot is the algebraic intersection number. So the number of points in L1 intersected with sigma 2, but with signs. So here would be an example. L1 is this trefoil knot. L2 has been drawn there. I will try to draw the surface for L2. Well, this one is not so hard. There's just one intersection point right here. And this intersection point has a sign. And in this case, I have the linking number of L1 and 2 is equal to +1. And this is symmetric. So this is actually a linking number of sigma of L2 and L1. Now this is a little bit hard to see if you see this for the first time, because you would have to find an oriental surface that bounds L1. And you could say, well, just take this band here. And it certainly pierces just once here. But that wouldn't be legal, because this band is actually not orientable. You would not be able to define a sign here. So in order to find a surface that bounds L1, you have to think a little bit. I can do it, but let's not do it now. But important, this is symmetric.
There is a simple recipe on the drawing for crossing counting, or you really
Yes,
have to
yes,
draw the
there is,
space?
there is. There are 1,001 ways to define it. I just give you one. So this would be an interesting example where actually linking number is 0. Because here you see this is your surface. It pierces twice, but with opposite sign. And yet they are linked. So this certainly describes the whole linking theory. Now here's an interesting example. These are the Borromean rings. They actually exist outside this building, somewhere out there in metal. What's interesting here is that all linking numbers, individual linking numbers, are 0. Which you can see. So the white one and the green one are actually not linked. And then I claim I can define this triple Milnor number. Triple Milnor number. So this is very old, very nice thing. So the way this goes is that this mu, so there is a little lemma that says if the linking number of L1 and L2 is 0, then you can find sigma 2 such that the intersection of sigma 2 with L1 is actually empty. Not just the same number of points with positive sign as with negative signs, is actually empty. So what you would do here, you would just say, okay, I take a little tube here, and I just do this. I walk along this surface all the way around along here, along this component. So I have these tubes. And now I have a surface of genus 1. So this new sigma 2 has the property that it does not intersect L1. So this was L2, this was L1. It no longer intersects it. And this is the general principle. And then the definition is you do mu of L1, L2, L3. Now you take the intersection of these three surfaces, sigma 1 dot sigma 2 dot sigma 3. So this will be some picture. Somehow you have now intersection of three surfaces. So it will generically you have some horizontal plane, some vertical plane. They intersect in some line. And then you have also a plane like this. And then there will be just this one intersection point, and it will have a sign. And you count these guys. That's the triple Milnor number.
Sigma 1 is the surface with boundary on L1 which doesn't cross L2.
Neither L2 nor
For
L3.
the others.
So I'm sorry?
So there's the cyclic definition. Sigma 1
Yes,
is the
yes,
one with
yes.
boundary L1 do not
Yes.
cross L2. And
Neither L2 nor L3. Yeah, you have to think a little bit, but it works. You have to do it sort of for both, and then for all of it. So I'm not even trying to draw this here. Okay?
which
But-
is, however, the easiest case possible.
Yes. Anyway, if I wanted to draw it, I would draw it somewhat differently. Anyway, the answer in this case is plus or minus 1, and this mu is skew-symmetric. So if you define that, if you say this is mu 1, 2, 3, then this mu ijk is skew-symmetric. And just believe me, I'm not going to explain. So these are two nice invariants. Where's the page? Did I want to say more here? No. And now we need one more. This is this Alexander-Conway polynomial. So Alexander, the Alexander version is really very old. Polynomial of a link. And again, oriented link. So this will be denoted by lambda L of z. So the variable is z. So I can write this as c0 plus c1z plus c2z squared plus etc. Each ci is an integer, and it's a polynomial in z. That's what it is. And for combinatorials, really the nicest way to define this thing is by a skein relation. So defined, but it's not obvious that this is well defined, just to say nabla of this crossing minus nabla of this crossing is equal to z times nabla of the smoothing. And so this is called skein relation. And then there's the other thing, it's normalization that says if you do nublic on an unlink, and it has m components as always, then this will be 1 if m is equal to 1 and 0 otherwise. So theorem, this is a well-defined procedure. So it's not the Jones polynomial, it's the Alexander-Conway polynomial. So, I mean, maybe you have seen this, but I will just show you that this actually makes sense. So here's a here is how you would compute this for a trefoil, and the computation is going to be useful. So there is this stick. I guess this needs to be pulled a little bit like this. So we try to compute it for this trefoil. I apply my skein relation here. So this is my trefoil. If I change that crossing, I actually have an unknot. So here the value is just 1. Then it should be z times what happens when I smooth. Now this has become a link with 2 components. But never mind, something has gone down. The number of crossings has actually gone down. So I start again. I compute for this link at this crossing. Well, if I do the other one, I have a trivial link. So this actually gives me 0. So it's equal to z times, and now this is again just an unknot. So here's 1. So the total answer is 1 plus z squared. And claim this, you can always do this. Now, well, there's an interesting feature of this, and that is for this 2-component link, the linking number was 1, and actually we found z. So for this this thing right here. And this is actually a general fact, but let me say something else before. So combinatorics people really like, I guess, would like this definition, but it has a drawback. And the drawback is I really needed to project my link on the plane to make a diagram, and in order to apply these relations. So there is the original, there's a topological definition. So topological definition of this nabla. And I will not do it, but somehow you just take the three-dimensional space, which is the complement of your link, and you do something with this. And it's manifestly a not invariant. This one you would have to prove that it's a not invariant, actually. And what it will give you is that this nabla L is really the determinant of something which you construct, some finite matrix. I will not explain. But what happens is that actually it will start, what you can see is it will start in degree m minus 1, the m minus 1 of L times z to the m minus 1 plus higher order terms. So for example, for this m component, for this 2-component thing, it would start in degree z, degree 1. And this Cm n minus 1, m minus, well, this is exactly the Laplacian matrix L. I take out a line and a column, and then, I'm sorry, the determinant of it, of course, is the determinant of this Laplacian matrix where I take out a line and a column, and for every xij, I have to substitute, I hope you can read this, the linking number of the i's and the j's component. I guess this is the way how one writes in computer science. So for example, for this 2-component link, we just have the linking number L12, which in our example was 1. So I would like to call this Lij. And indeed, so it means the coefficient of z is just the linking number, but then there are higher ones. And so this really comes out of the topology. It comes out as a determinant. But of course, we know there is this Kirchhoff formula. So we know it's something about spanning trees. And in fact, this was already known to people, I mean, many years ago. So people who discussed this, they knew it's Hosti and Hosokawa and these people. They knew you can write this as a sum over spanning trees labeled by these linking numbers.
Excuse me, I missed that. Do you really mean higher order terms or lower order?
Higher order terms. So higher powers of z. So you see, if if this thing already says if it has m components, it's a trivial link, it's actually 0. Now, if you try to introduce some crossings,
Every time you get a
you cannot get any power of z lower than m minus 1. Think about it. So, so this is, and I mean, this was really the starting point for our work. So, anyway, so then the next thing is I'm running out of white chalk. I guess this one. Okay. So the starting point for what we did was actually the following theorem of Levin. And I understand he says it can be, as he says, culled from work of Traldi. But I don't really know. Certainly Levin gives a very nice geometric proof of this, which says that if all Lij, so remember these are these linking numbers of Li and Lj, are 0, then actually this nabla L of z will start in a much higher degree. The first term will actually be twice as high, z to the twice n minus 1 plus higher order terms. And this one will be exactly with the determinant of this matrix I called lambda. Again, I take out a line and a column. And for this Yijk, I have to substitute the triple Milnor number mu of Li, Lj, Lk.
Okay, so all Lij's are 0.
All Lij's are 0, yes. So this is what he says. And again, this follows from this topological definition. In fact, for those of you who know this topological definition, this is somehow made out of the Seifert form. And in this Seifert matrix, you can find, I'm sorry, I should have said this here, so let me not say this. Anyway, this is what he says. And so, of course, we were wondering, well, I mean, in fact, he asks, is there a spanning tree interpretation of this? So we played with this a little while, and we found this, this spanning tree theorem. But in fact, we are going to give a new proof of this result using finite type invariance. So I have still, I guess, 15 minutes. So let me show you a little bit of stuff. I guess I will not be able to. Yes, that's what I will try to show you, if I can. But it comes out of quantum topology.
You mean determinant of Pfaffian?
I'm sorry?
There is that.
Well, we will see if I get there. So,
The theorem has determinant in it?
this theorem has a determinant in it, yes.
So it's the square of the Pfaffian.
So which is going to be the square of the Pfaffian.
So you've actually gone a little beyond that.
Yes,
Computing
yes,
that,
yes,
you got an
yes.
extra-
Well, I mean, everybody knows the determinant of a skew-symmetric matrix is the Pfaffian squared. So I'm not really claiming any originality there. So what happens is that Cn is a finite type invariant of order n. So whatever that means. Now, what then happens is there is a general theory. In fact, if you know what it means, it follows immediately from these gain relations, but never mind. Now what happens is I can take a sort of space of chord diagrams. Which I denote by A of degree n, so degree n. This just means n chords, an on m, or something I would have Q vector space generated by things where I have these my m circles, like this. And then I put m chords. So let me use this yellow, although it's really the same. I put some chords on it, for example, like this, whatever. So this would be degree 1, 2, 3, 4, 5, 6. And then there are some relations, which I'm not going to give you now. And it's really amazing that when we actually don't know the dimension of this space.
They must connect everything?
No. Anything. Anything is allowed. Now what happens is, and I will, because I have no time, I will just cheat a little bit and give you something that's not strictly speaking correct. But it's correct to lowest order. And I guess with physicists in the audience, this is already very good. Sorry, I take that back. Anyway, sometimes I feel frustrated because I don't understand physicists talk, and there is clearly something very interesting going on in their talks. But anyway, so I will just so theorem Kontsevich. So there exists sort of a universal finite type invariant of links Z, which is a power series Zn of L, and this Zn of L takes values in this space of diagrams, which unfortunately we don't even know a dimension of when n is big. And then the corollary of this is that sort of fact, there exists a linear form Wn. So this is just a linear form on this space An. So I just write it like this. I guess I should write In of M dual, such that nabla L of Z is just the sum n equals 0 to infinity of this Wn applied to this Zn of L, Z to the n.
That is a number or a polynomial?
This is some, sorry, which one? Z? Z is some vector in this huge vector space, but finite dimensional.
So
So it's a collection of chord diagrams. So physicist Luranski would say this is somehow done of GL of some U11 or GL11 Chern-Simons field theory, but let's not worry about that right now. So something like this. Now I claim you can actually understand this weight system. So this W is called weight system, since this, so this is called weight system. And is so the terminology is the weight system of the Alexander-Conway polynomial. So what happens is you can compute this recursively. If you have Wn, so this thing, if you see some diagram that has n chords, this is where this Wn is supposed to be defined. But I just focus on one chord. So this is just some piece of my n circles. Could be the same circle, could be different ones. And just focus on this chord. It says it's really Wm minus 1 of the thing where I just do what we would call a surgery. Do this. So in this case, the number of circles has actually changed, either increased or decreased. But the number of chords has gone down by 1. This was an n. So using this, you can compute recursively, because at the very end, when we go down to no chords at all, you will see a number of circles. You don't know how many, let's say k. And then the answer is again, it will be 1 if k is 1 and 0. So this I just write 0 otherwise.
this is a question which is 1 plus z square order.
I'm sorry?
Is that you say?
No, this follows immediately from this gain relation over here. If you understand how a chord is related to one of these crossings, you actually see here, it follows from this gain relation. But I will not do this now. I just believe me, this is the recursive computation of this Wn. And now, when I see this, I see spanning trees. You see? Now we are in business. Suppose you try to evaluate this thing on diagrams that live on m circles. So this leads to spanning trees. So suppose you have, say, just for simplicity, 4 circles. So you have a 4-component link. And you have some weight system, and say you take n, which is less than, so this was m equal to 4. We take n strictly less than m minus 1. It means in this case you have only 3 chords you can put. So whatever you do, however you put your chords, you can never connect everybody. So you will get W0. So Wn will be identically 0 on any diagram if the degree is less than m minus 1. I have 4, so I would be allowed 3 chords. No, I'm sorry, 2 chords. Yes, 2 chords. Yes, thank you. If I have 3 chords, I can do something. For example, I can do this. And then when I do my surgery business, I will get down to 1 component. You see, then it actually becomes something like this. This Wn W3 of this becomes W0 of, and now I just do the surgery. Okay, I mean, you get the idea, right? Of this, and this is one. So finite type invariants give me spanning trees, and topology gives me determinant. Now, I didn't explain, but believe me. So that's really nice. So the classical matrix theorem is really some property of the lowest term of the Alexander-Conway polynomial viewed in two different ways. So I thought this was nice, and so this is what we try to understand for this next term, this Levine business, which unfortunately was wiped out. So how does it generalize? So luckily I prepared something. So we have to upgrade, we have to become a little bit more technical, but I mean we are almost at the end of my talk, right? So we talk about something I call Jacobi diagrams. So now, instead of doing chord diagrams, I will allow these green things. So they could have internal trivalent vertices. So again, physically this corresponds to Chern-Simons, I mean trivalent phi cube or whatever. Don't really understand this. But I have diagrams like this. So instead of having chords, I have diagrams like this. And then the space of Jacobi diagrams, well, it will be all these diagrams modulo some relations. I have a notion of degree. The degree is 1/2 the number of vertices. So that would fit if it were chords. Every chord has 2 vertices. So unitrivalent diagrams, I have univalent vertices here and also trivalent vertices on the inside. And I have these cyclic orientations. But the relations say that if I change the cyclic orientation, I just get a minus sign. So usually I have a convention, I don't draw the cyclic orientation, it's always the canonical one. I have this called STU relation, which sort of defines what a trivalent vertex is in terms of chords. And this 4-valent thing is not there. This thing is completely abstract. It's not embedded anywhere. And this is the so-called Jacobi or IHX relation. And what this thing is really engineered to the following, but I will not really have time to get into this, to define linear forms from it, which come from Lie algebras. And in this sense, Alexander-Conway corresponds to GL11, and that I understand. But anyway, so the fact is that this space AN of M is actually isomorphic to this Q of Jacobi diagrams of degree n. And again, then modulo these 3 relations, antisymmetry, STU, and Jacobi. So in other words, in fact, if using these relations, you can expand every trivalent vertex in terms of chords. And I claim you get exactly the same space. But now, with these things at our disposal, we can talk about diagrams that somehow look like this, like my edges of my 3 graphs. And so what happens is there is a fact, which I don't really have time to explain, but somehow there is a way. So this weight system, comes from this Lie superalgebra GL11. And there are very old papers by Kaufmann, Saleur, or Rosansky about this, which I never understood. But then with this new technology, I mean, not so new anyway, actually, I can make some sense out of this, and I will not explain how from a Lie algebra you get a linear form right now. But anyway, so this gives me some way to get at these milnor numbers because of the following fact. So it's a theorem, in fact, which I proved with Habiger some time ago, is that actually milnor numbers correspond somehow to coefficients of tree diagrams in this well, just tree diagrams. And in fact, the way it stands, it doesn't apply here, but this is really for string lengths. So it means it doesn't actually describe for links. So there's some problem with these Milnor numbers because there is this problem that they're only defined if the lower ones are 0. So the mu ijk could only be defined if the linking numbers were 0. And so, but in any case, somehow we would say that such a diagram here with Li, Lj, Lk, somehow it is weighted by this Milnor number mu ijk. Now what happens is that using this technology of this weight system, you can somehow show that the coefficients, so if all Lij are 0, then the coefficient C2m minus 1 comes from diagrams in Z2m minus 1 of L, which consist of exactly m minus 1 of these y's. So let's do the easiest case. Let's do m equal to 3. So I have 3 circles. And now I try to put exactly 2 of these guys on it. For example, I could do this. I could do this one here, and then this one. Remember, there is no 4-valent vertex here. And this then would somehow give me the term mu123 squared, which is indeed my P3 squared. And now if you think about it, because of this STU relation, there's really nothing else you can do. So if you have just you have a circle, and you put on this something like this, and here it continues on the right, then STU will tell you, well, this is this, like this, minus the same thing where they cross. But everything is abstract. So there's no embedding anything. So this is 0. So somehow this diagram is the only one that can be non-trivial.
So these links are not oriented.
Yeah, they are oriented. But it doesn't matter anything. It doesn't matter, believe me. So the only way I put 2 of these guys in such a way that it's non-zero right away is in this fashion. Of course, there is some symmetry, but they all give me the same number because of the anti-symmetry of these mu ijk's. So what is the general story here? How do I get to the Pfaffian tree polynomial in the remaining 1 minute, or 2 minutes, I guess. I started 5 minutes late, huh? So I guess I won't have time, but I just show you what happens. So if you understand this Lie algebra business, you can find some relations for these for this weight system W of GL11. And so, for example, this corresponds to some property of the Lie algebra. This corresponds to the fact that the Lie algebra is solvable, stuff like this. Somehow, all I want you to focus on is this corollary here. We have a picture like this. Imagine we have M of these circles, and now we have 2 y's, and there is no other y somehow sitting on this circle. Then it says I have a reduction like this. I can replace this y just by simple chords. So in some sense, I have decreased the degree by 1, and I also have decreased this number of circles by 1. So it follows from this one together with this one, or something like this. Now let's think about a second. We have, according to what I claimed here, we have m minus 1 of these guys. They have 3m minus 3 endpoints. The total number of circles is m. There must be a circle which has exactly 2 endpoints, 2 of these y's. Because nobody can have just 1. It would be immediately 0. So I can, using these relations, recursively evaluate Wm of these diagrams. So here should be a W2 m minus 1 of these diagrams. And now I claim this is going to be, the claim was that this was going to give me the Pfaffian tree polynomial squared. But it's the same story. When you look at the Pfaffian tree polynomial squared, again, so we have this Pm squared, so we have something like y1, 2, 3, y3, 4, 5, plus, etc., squared. Again, because it's spanning, every vertex has to appear at least once here. So in every monomial you have here, every vertex has to appear at least twice. On the other hand, there must be a vertex which appears exactly twice, because we don't have enough. Same argument as before. So it means that if I now assume that I take some monomial in here, it will contain something like, say, y1, 2, 3, y1, 4, 5, for example. And then product of other things. And there's no other things, but there's no 1 here. Such a thing must exist. Now I do my contraction deletion business and just take out this 1, 2, 3 and this 1, 4, 5. I mean, I'm not going to do it now. But you see, I'm going to get some kind of formula. And in this end, it just matches up perfectly with this one. And so in this way, I will get that, so after some combinatorial things, because it depends on whether they are distinct or maybe they are the same. I mean, these 2, 3, and 4, 5 could actually coincide. Anyway, so at some point, I somehow get that this C2m minus 1 is indeed this Pm squared in the triple Milnor numbers mu ijk. So this is how it comes about from this finite type invariant business. So in fact, this gives you another proof. But of course, it's a complicated proof. I guess this is basically my talk. How does it generalize this whole thing? So we have something for higher order Milnor numbers. Malek has this thing where he generalizes to somehow things which correspond to polygons, but somehow it would mean in my language it would be something that's completely antisymmetric. It would have, say, in this case, 5 vertices, but it would be completely skew symmetric here. And from my point of view, this is not good enough, because the Jacobi diagrams on these 5 vertices, there's not just a one-dimensional space. It's only for 3 that it's a one-dimensional space, this lambda 3. But if somehow the Jacobi diagrams sort of on 5 vertices like this is not one-dimensional, and you have to somehow deal with this when you want to go to higher things. But anyway, so there is some generalization. And the hope was, in fact, that there would be some kind of even more fantastic Pfaffian polynomial for higher trees. But we didn't find it. And maybe it doesn't exist. Maybe there's only determinant in Pfaffian. I don't know. But thank you for your attention. And,
Questions?
Well, does there exist an Alexander-Conway polynomial in a further variable?
yes,
which
yes.
If you have
You can take a variable for every component. It's called a multivariable Alexander polynomial.
Sorry?
I can take a variable for every component of my link. It's called the multivariable Alexander polynomial. It works the same.
If you can have such, relax this 1-0 weight in such a way that you take x to the m minus 1.
I'm sorry? Say it again?
Can you, such that when you have m unlinked nodes, in the definition, sorry.
In which definition?
In the Blackboard definition of Alexander-Conway.
Here? Yes.
The second one is such that you have, instead of 1, lambda to m minus 1.
Yeah, I mean, it will be some specialization of the multivariable one. But let's maybe discuss this in private, because I think people want to, we have to go to this photo opportunity. But anyway, there was another question.
Yeah, let me just ask quickly. So there is this, so if I understood it well, you proved that for links, this weight system,
Yes.
the leading term of
Yeah.
the weight system is determinant, right? Or Pfaffian or the
Yes.
interpretation. So
Well, under the hypothesis that certain diagrams don't play a role. So this was under the hypothesis that in my conservative integral there are no chords.
So there is this, I know that this Barnatan and Gerufal
Yes.
interpret
Yes.
the leading term as determinant.
This is really for knots,
It's
though.
that was the question.
Yeah,
so
yeah,
they deal
yeah.
with knots.
Yes,
Okay.
yes. Yeah. This doesn't tell me anything about knots. This is a query for links. I mean, I have something of knots too. Maybe yes?
So these spaces C and M, we don't know the dimension.
Yes, and this would be really something great if somebody could do this.
I have a question related to that. When you pick, so if you pick any group SUN or something,
Yes.
and you have a map from this,
Yes.
do you have a projection map into some representation of the group?
In some sense, yes. So what you really have to do is you have to take a Lie algebra, and then for every component of your link, you have to have a representation. And somehow these relations STU, which have somehow gone away, told you that this is somehow you can evaluate using such a diagram. And Vogel showed that there are diagrams which cannot be detected by these Lie algebras. So there is something we really don't know. And so there are lower bounds on the dimension because you can detect lots of things using Lie algebras, and there are upper bounds because, for example, it's just the number of chords. That's certainly known. But we don't know the dimension. I think for n equal 10, we already don't know the dimension. Or certainly for 13, we don't know the dimension. So Barnatan is the best computer, has the best computer results, and later we don't know. So it would be very nice. I mean, it's just a linear problem. I mean, I gave you these relations. It's just a linear problem.
Sometimes to determine, like I was thinking of like spaces of invariance.
Yes,
when
yes.
you don't know the certain
This gives you lower bounds.
different things.
This gives you lower bounds.
Because I was hoping that by increasing the dimension of the n, the
Mhm.
SUN, for instance, maybe one would not get more relations due to this projection than what was already there at the graphical level.
By the way, I would like to, since he said, I would like to apologize. So I mean, certainly he has nothing against lambda 3 and S2 and so on. I was just joking because we had a discussion this morning.